Everyone knows the importance that science attributes to the light emitted by celestial bodies, especially stars. Light, this little word, encompasses all other forms of electromagnetic radiation. The considerations that science makes about the behavior of stars and the galaxies they form depend on this tool. It would be impossible for a manned spacecraft to reach Alpha Centauri after the Sun, the closest star to us, to know what was happening in real time with its possible planets. Imagine reaching the Andromeda Galaxy, located more than 2 million light-years away. Our inevitable dependence on the information that light carries attributes to light the function of messenger of space. As a consequence, no event that occurs in the visible universe could be described directly, including space itself. For example, in order to see a subatomic particle, such as an electron, it must first be illuminated. The light that stars emit into space is translated by our senses as being white, or composed of a mixture of all the colors of the spectrum. That is, it would not be polarized, since there would be no notable separation between ultraviolet and infrared. This finding is compatible with the statement of the theory of relativity, which tells us that the speed of light is constant and does not depend on the movement or immobility of the source in relation to the observer. Thus, if light were used as a tool for measuring distances in time, the relativistic contraction of the length of space and the consequent dilation of time could not be measured directly by the Doppler effect of light. There would be, in white light, a virtual leveling between all its energy levels. Taking this detail into account, physics assumes that the light from a distant star would move away from the source in the form of circular waves, in which all its wavelength bands would move at the same speed of 300,000 kilometers per second. When light passes through a prism, it stops being white and becomes polarized, revealing a beautiful rainbow containing all the colored bands of the visible light spectrum. The waves with the highest energy move towards the ultraviolet, and those with the lowest energy move away towards the infrared. This property of light, being polarizable, was the first step taken by physics towards the Doppler effect. The second was to associate the behavior of light with that of sound, since both would be formed by continuous waves. When a train approaches an observer standing at a train station, the sound becomes higher pitched, even though its frequency remains the same for the train driver. The sound waves contract. When the train moves away, the waves stretch, and the sound becomes lower pitched, only for those who remain still at the station. For the Doppler effect to become viable as an instrument for measuring distances in time, light waves would need to be continuous, like sound waves. The discussion about the possible discontinuity of light waves was spawned by Planck's work with electromagnetic oscillators, and it was consolidated by Einstein's work with the photoelectric effect. That is, the coetous nature of light would attest that it would be discontinuous. Thus, Einstein postulated that light would travel through the vacuum in the form of small isolated packets of energy, which he called photons, and not in the form of waves. Furthermore, the photoelectric effect considers that the light that falls on a metal plate would have a shorter wavelength than that of the light scattered after the collision. This scientific data allows us to assume that the Doppler effect would be exposing the separation between ultraviolet and infrared, polarized light, with a delay, or at the moment when the light would already be depolarizing and becoming white for the observer. This problem would arise from the necessary quantization of light revealed by Planck's oscillators, and whose nature would be timeless. Classical physics assumed that when an electron collided with a metal plate, it would absorb energy until it could make its quantum leap. For this to happen, it would need a certain amount of time. However, in the 1920s, it was experimentally proven that no amount of time would separate the free electron from the live scattered bind. That is, as a unit of energy, the scattered quantum would be delivered, ready, to the observer. When a quantum collides with a free electron on a metal plate, both appear simultaneously. The electron recoils, and the quantum scatters. If light were not packaged or quantized, our tracking devices would not be able to capture it, and light would become invisible to us. According to the prediction of classical physics, the light emitted by a star would move away from the source in the form of circular waves, and should appear, to us, as white or depolarized. Thus, everything indicates that the polarization detected in the Doppler effect and expressed in the separation between ultraviolet and infrared would have had to have occurred during the timeless packaging of light. In other words, before the light spread out at our position. When it comes to our subjective assessment, it would be as if the quantization had stretched and polarized the light at the future point. During the process, the ultraviolet and infrared would have come to occupy the opposite ends of the visible light spectrum. Due to the timeless nature of quantization, the redshift could not be detected directly or in real time, as is seen in practice when using the Doppler effect. This is because, if quantization did not require time, there would be no movement that could be measured directly. At least, until the moment of the photon scattering. Therefore, the light from the stars is delivered to us as being white, a color resulting from the mixing and energy leveling of all the colors of the spectrum. This interruption in the flow of light photons, related to the timeless nature of quantization, would isolate the redshift of the radiation at the future point. It could not be detected directly by anyone observing from within the visible universe. From the observer's point of view, this would result in the apparent continuity of light waves. In this case, despite appearing otherwise, our memory should be acting in a discontinuous manner. This apparent continuity of light waves would be behind the concept of isotropy of space-time, since, being continuous, they would no longer depend on the direction of their propagation. For our subjective assessment, and only for it, the light from the stars could be arriving from the future, as well as from the past. If the light had been polarized at the future point, by following its timeless packaging, what we see directly in the past of the celestial vault would become a mirrored and inverse image of what would have occurred in our future. This implies that the inflation detected by Doppler could not be occurring in real time. Since the information contained in the light from the stars is made available to us by circular waves of uniform movement composing white light, this would put the Doppler effect in check. In other words, the circular waves would be giving us information that would not be compatible with our uniformity. The Doppler technique would be showing us a series of photographs of our past being exposed frame by frame in the celestial vault after hidden gaps in the flow of time. Thus, the redshift and the expansion of the universe suggested by it should not be happening in real time.